Assalamualaikum warahmatullahi wabarakatuh and very good day. Today we are from Group 1. We are presenting the flow dynamics around Jabulani Ball World Cup 2010. Moving on to the problem statements. The Adidas Jabulani Ball, introduced in the 2010 FIFA World Cup, was widely criticized for its unstable and unpredictable flight. Only 8 thermally bonded panels and a smoother surface than traditional 32-panel balls. The design reduced surface roughness, affecting airflow behavior. This caused delayed flow transition, aspiration, and an unsteady wake, leading to the knuckleball effect even with minimal spin. Our first objective is to generate the CFD result and analyze the lift and drag profile of the ball at various speeds. And secondly, we want to identify the design factor contributing to the unpredictable motion. The geometry of solid bodies of Jabulani ball and the traditional soccer ball were made from Autodesk Inventor.
Here we can see the key variation between the 8-panel Jabulani and the 13-2-panel classic football. The Jabulani, introduced in 2009, has only 8 thermally bonded panels with a 3D propeller shape made from PU, AV and textile layers. It has a very shallow seam depth of about 0.1 mm and a grip and groove surface texture designed to improve grip and control. Meanwhile, the classic ball, used in 1916, has 32 stitch panel, 20 hexagon and 12 pentagon, with deeper seams of 2 to 3 mm. It's made from PU, PVC and rubber and has a smooth surface, giving it a more stable and predictable flight. Both balls meet standard weight and size regulation. The Jabulani weighs 414 to 445 grams with a circumference of around 69 cm, while the classic ball is slightly heavier or lighter and measures about 16.8 to 17 cm.
So the next part is mesh and grid. After we put the geometry of Jabulani ball into the geometry section in CFX ANSYS, we generate the mesh using ANSYS meshing. A tetrahedral mesh was applied to the fluid domain to handle the complex shape of the ball, especially around the seam. We used finer mesh element near the ball surface and added inflation layer to accurately capture boundary layer effects. The outer domain was meshed more closely to save computation time. Mesh quality was checked to ensure a good squeakiness and orthogonal values. In total, our mesh contained around 500,000 to 2 million elements, providing a balance between accuracy and efficiency. After we do the mesh, we proceed to the ANSYS CFX-free. In ANSYS CFX-free, we define the boundary layer and initial condition for the simulation. First, we set the inlet and outlet of the flow domain. The inlet was assigned a uniform velocity of 30 meters per second, while the outlet was set to static pressure 0. Next, the ball surface was defined as a no-slip wall, meaning a stick to the surface. Finally, we apply the necessary physics setting, including flow direction and turbulence model, to ensure accurate simulation of airflow around the ball. So the last thing we need to do is to get the result. Uh, with the result, we choose the streamline to to get the flow around the Jabulani ball. So this is for a view that we got and we screenshot from the result to show you about the streamline at Jabulani ball. After we do the setup, we got the four graph in the solution. The first graph is the about wall and boundary scale. The second is about turbulence graph. The third is a plot normal velocity at x-axis, y-axis, and z-axis. And lastly is the graph about momentum and mass. So this is our animation of Jabulani ball. So this is our animation of Jabulani ball. So this is our animation of Jabulani ball.
Analysis and comparison. The drag coefficient for traditional ball is 0.18 while Jabulani ball is 0.22. This indicates higher aerodynamic resistance for Jabulani. For velocity controls, traditional ball shows smoother flow and narrower wake region, while Jabulani ball exhibits earlier flow separation and larger wake reducing stability. For pressure distribution, traditional ball has symmetrical pressure zones, aiding in stable flight, while Jabulani ball shows higher and uneven surface pressure, especially at the rear. For streamline patterns, traditional ball produce predictable airflow, while Jabulani ball demonstrate irregular and transient flow behavior even in steady conditions. Now, for the conclusion part, the Jabulani ball demonstrates aerodynamic behavior similar to a near-perfect sphere. CFD simulations show that the Jabulani experienced earlier flow separation and larger wake regions due to its smoother surface and shallow seams. The traditional football design promoted more stable airflow with symmetrical pressure distribution and delayed boundary layer separation. The unstable flow behavior around the Jabulani supports reports of unpredictable flight paths and knuckleball effects during gameplay. Surface geometry and seam design play a critical role in influencing aerodynamic stability, affecting both drag and lift forces. And lastly, future football designs should consider optimizing surface features to balance performance, predictability, and player control.